announcement. No class on 22 November. And I think it's going to be third quiz, right? 29 November. And after quiz, probably we have one more class, and then we are getting into December, so it's a final week, final exam. So depending on the schedule or progress, we may have one or two classes after today, and then we are going to have a final. So probably it may be best for you to repeat or review what you have done last week. So we are going to continue the discussion about generalized partial differential equations. So x, y, independent variables. Z, dependent variables. So basically we are considering two-dimensional space-time partial differential equations, and maybe it may have one more degree of freedom for the time. So P, x, y, z, partial x, partial z, plus q, x, y, z, partial y, partial z is r, x, y, z. This is the most generalized form for the partial differential equation, the first order. And I told you that it does have a name. It's called Lagrange's equation. Last week we considered the very equation, which is describes a solitary nonlinear wave, the propagations, and it's like you need to have experience in playing with derivative, right? It's like a game. So you need a little tricks. You need to learn about how to make a derivative for like dependent variables. Chain rules is especially one of the techniques that you need to use freely. So I'd like to state one theorem that if u x, y, z equal a and free x, y, z is b are two independent solutions of an ordinary differential equation. by P x y z dx q x y z dy r x y z dz. Then there is an arbitrary function phi u v such that p partial x partial phi q partial y partial phi r partial z partial phi equals 0, and from this we can find z x y such that p partial x partial z plus q partial y partial z is r if and only if partial z partial phi is non-zero. It seems like we have 3 different pandemics. One is COVID, still around, and new flu, right? 독감. And there is another one called Chinese pneumonia. Pneumonia is 폐렴. 중국발 폐렴 is also around, so I think you probably should be more careful. So, theorem states that this is 0, right? So, let's find out which condition that this under which condition that this equation becomes 0. A theorem that if there is a solution u and v from this differential equation, then we obtain this is 0, right? So we proved half of the theorem. Consider phi u v, a general function, is phi u x y z v x y z. So you need to know how to apply the chain rule. So partial x partial phi is partial u, partial phi, partial x, partial u, partial v, partial phi, partial x, partial v, right? How about partial y? Partial y, partial phi is partial u, partial phi, partial x, partial u, partial v, partial phi, partial y, partial v, partial z, partial phi, partial u, partial phi, partial x, partial u, plus partial v, partial phi, partial z, partial v. up to this, you should be like able to do this chain rule. So this is called the chain rule. I think probably you have learned the chain rule for the first time in high school, right? And then again at the freshman calculus or freshman 미적분. Then the one. So P partial x partial phi Q partial y partial phi R partial z partial phi is simply, let's put together everything. Partial u partial phi partial x partial u partial v partial phi partial x partial v Q partial u partial phi partial y partial u partial v partial phi partial y partial v plus r partial u partial phi partial z partial u plus partial v partial phi partial z partial v. So let's try to have a common factor u first. Then we have partial u partial phi p partial x partial u q partial y partial u r partial z partial v, and this is a common factor too, right? So we can have partial v partial phi p partial x partial u q partial y partial v r partial z partial v. This is v. Another statement in the theorem says that you need time to copy. I think to wake me up. Am I loud enough? You can hear me? Where? No problem at the end? Okay. So, on that to here. So it looks like that P round x round phi plus Q round y round phi plus R round phi round z is actually, this is 0, right? And this is 0. So this whole thing is 0. And according to the statement is that we have dx over p, q over dy, r over dz, and we have u, x, y, z is a, and v, x, y, z is equal to b, right? So that is u, x, y, z is a is constant, right? So this is a solution surface. That is, we have x, y, z. this is x, y, z. This is the solution surface. It's called. So on this surface, we can choose another point. Right? So this is a surface that u is constant. Then at this point, u, x, y, z is a, right? How about at this point? ux plus dx, y plus dy, z plus dz. Still u is constant, right? So u should be a. That is u x plus dx, y plus dy, z plus dz is also a, right? Because u, x, y, z is a solution surface. Either this point or that point, this equation should be the same. So we can subtract. Oops, what happened? Plus what? dy, z plus dz minus u, x, y, z is equal to 0. Or u partial x partial, no. That is partial x partial u dx partial y partial u dy partial z partial u dz is equal to 0, right? From this too. And we can have another surface. V is B. Then likewise partial x partial v dx partial y partial v dy plus partial z partial v dz is equal to 0. Check my notes. So the condition is P over dx Q over dy is equal to R over dz. We have U x, y, z is A, V x, y, z is B. And from this we have two equations, partial x, partial u dx, partial y, partial u dy, partial z, partial u dz is equal to 0. And partial x partial v dx partial x partial v dy partial z partial v dz is equal to 0, right? By the way, p over dx is q over dy is equal to r over dz. We can say some lambda. Then dx is p d lambda, right? dy is q lambda, dz is r lambda. So if we substitute this into this, then we obtain partial x partial u lambda p partial y partial u lambda q partial z partial u lambda r lambda p partial u partial x partial u partial y partial u r partial z partial u is equal to 0, and partial x partial v lambda p partial y partial v lambda q partial z partial v lambda r. So again, p partial x partial v q partial y partial v r partial z partial u is equal to 0 for every lambda. So if this condition is supposed to be satisfied for every lambda, then what is the condition? The equation inside of the parenthesis is 0, right? Partial x partial u p partial y partial u partial z partial u is equal to 0, and p partial x partial v q partial y partial v r partial z partial v is equal to 0, right? One English word, this is called parenthesis. This is called brace. This is called bracket. So you learn extra vocabulary while learning mathematics at the same time. It's called one stone, two birds. 일석이조. Then you can go back. Therefore, P partial x partial phi, Q partial y partial phi, R partial z partial phi is equal to 0. So this is another solution surface, UV, is constant. Phi x, y, z. This is called phi uv is constant. Then if we take a partial derivative, what happens? Because this phi is x, y, z, x, y. This is partial x, partial phi, plus partial z, partial phi, partial x, partial z, right? And likewise, partial y, partial phi is partial y, partial phi, plus partial z, partial phi, partial x, partial z. Is equal to 0, is equal to 0. Therefore, partial x, partial phi is minus partial z, partial phi, partial x, partial z. Partial y, partial phi is minus partial z, partial phi, partial y, partial z. We substituted it into this equation. P minus z phi partial x partial z q minus partial z partial phi partial y partial z plus r partial z partial phi is equal to 0. So it looks like this is common factor. So you can put them together. Partial z partial phi minus p partial x partial z minus q partial y partial z r is equal to 0. And this equation is supposed to be 0 for all this partial phi partial z. Then this should be 0, right? So we have minus partial x partial z p minus q partial z x partial y partial z plus r is equal to 0. Or we have p partial x partial z plus q partial z is partial y is r. That's the original equation, right? So before we do some examples, maybe we can take a few minutes break. So, since we have proved the theorem, made a statement about the theorem, and also we proved that, I'm going to give you the process how to solve the differential equations. P partial x partial z plus q partial y partial z is equal to r. Step 1. Find u is a, v is b from p over dx, q over dy, r over dz. Step 2. Form an arbitrary function phi u free is constant. This is a solution surface. Or or you can say u is psi v. Either way is fine. So you first find the solution. So u and v is from this equation. And then from this equation, u and v, you just form a solution surface that such that phi uv is constant, or you can say u is from psi v. So step 1, just say dx over p, q over dy, r over dz. You can also, it is LP, MQ, and R, LDX, MDY, and DZ. Of course, L, M, N, just some number. This is called theory of proportion. Let's check if this statement is true. So let's check. So if P over dx is L, P, MQ, and R, L dx, MDY, and dc. Then the first statement is true. Let's check. So we just simply LP, MQ, and R, LDX plus MDY plus NGZ minus P dx over P. P, LP plus MQ plus NR. Then P, LDX, MDY, NDZ minus LP plus MQ plus NR dx, right? P, LP plus MQ plus NR. What happens? PL minus LP dx. P dy minus Q dx over M plus P dz minus R dx n, right? This one is 0. From P over dx is Q over dy. We have Q dx minus P dy is equal to 0, right? This makes this is 0. P over dx is R over dz. r dx minus p dz is 0, right? So that makes this is 0. So this is 0. So we just proved that therefore P over dx is LP or MQ and R LDX plus MDY and DZ, right? But actually, this is supposed to be Q over dy and R over dz, right? I mean, from this and this, right? So therefore we have P over dx, Q over dy, R over dz is, you can say LP, MQ, and R over LDX plus MDY and dz. And this is called theory of proportion. So this is a very useful formula. For example, so you can accept the statement of theory of proportion, right? So let's do some example. Y plus z partial x partial z, x plus z partial y partial z is x plus y. So this is P, this is Q, this is R, right? So step one, what do we do? Y plus z over dx, x plus z over dy, x plus y over dc. It's supposed to be the same as this, right? We can actually add them together. Y plus z using P plus Q plus R dx plus dy plus dz the same as also dx minus dy P minus Q, right? You can say it this way. P plus Q plus R is equal to y plus z, x plus z, x plus y is twice of x plus y plus z. P minus Q is y plus z minus x plus z is y minus x. Also, dx minus dz, P minus R. P minus R is y plus z minus x plus y, z minus x. So actually, according to this is LP MQ plus NR LDX plus MDY NDZ. So this is the theory of proportions. So you can say LMN is all equal to 1 when you have a PQR, right? If we say L is equal to 1, M equal to minus 1, N equal to 0, then we have P minus Q, dx minus dy, right? And likewise, we can say L equal to 1, N equal to minus 1, and M equal to 0, then we have this equation, right? So this is probably the most easier way to handle. So maybe next page. Copy and paste. Y plus z over dx, x plus z over dy, x plus y over dz. So first equation, we have twice of x plus y plus z, dx plus dy dz is actually twice of x plus y plus z, dx plus y plus z is equal to, let me say, y minus x dx minus dy minus x minus y dx minus y. If we integrate this, what do we get? One half ln x plus y plus z is minus dx minus y plus some constant ln, right? Or ln x plus y plus z plus twice of ln x minus y is some constant can say u is x plus y plus z, x minus y squared is C1. This relation is useful, so maybe I can use it next page. Copy, paste, paste. Maybe I should be, oh, be a little bit more careful. Minus, and this may be tx minus tz minus x minus z minus x minus z dx minus z. So from this we can have ln x minus y minus ln x minus z is constant, or ln x minus c over x minus y is constant. From this we can say v is equal to x minus c over x minus y is c2. Therefore, phi x plus y plus z x minus y squared x minus c x minus y is 0. Is the solution? Or x minus c over x minus y psi x plus y x minus y squared is also solution. So we can properly use this variable proportion to find the general form of the solution. And let's do another example. X partial z, y partial z is z. And parameterize the solution. Surface. We have x equal t, y equal 2t squared plus t, z is 1 plus t to the cube. So this is the condition for determining the arbitrary function. So we can write down the p is equal to x, q is equal to y, r is equal to z, right? So x분의 dx is y over dy, z over dz. So we can have first dx over x is z over dy, dz, sorry, dz. So ln z minus ln x is constant. My handwriting becomes strange. Constant. So x over ln z is constant. We can say u as z over x is equal to a. Another condition, dx over x is y over dy, ln y over x is constant, over v is y over x is constant b. So we say u is c over x, v is y over x. So we can say u is some psi v, or z over x is some function psi y over x, right? We have z over x is some psi y over x, or z is x psi y over x. Under the condition that z is 1 plus t cubed, x equal to t, y is 2t squared plus t. So v is actually y over x. So you say t over 2t squared plus t, 2t plus 1. Let's say something w. Over t, w minus 1 over 2. Then z, 1 plus t cubed is 1 plus 2 over w minus 1 to the cube. X is t, so that is P W minus 1 Y over X is W, right? That is free. So actual solution is one plus 1/2 W minus 1 cube is X is 1/2 W minus 1 psi W. Copy. Then paste. So therefore, psi W is 1 over 4 W minus 1 over square plus 2 over W minus 1. And W is actually Y over X, right? Free. Z is X times psi Y over X, right? So this is X times 1 over 4 Y over X minus 1 to the square plus 2 over Y over X minus 1 is X times 1/2 Y over X minus 1 square plus Y minus X 2X. So very interesting. If we have a parameterized form for the solution, then we can exactly solve the partial differential equations, right? So parameterized solution is a way to fix the constant or fix the arbitrary function. Any questions? So actually solving partial differential equation, you need a lot of tricks, small tricks. Maybe you can have another example. Slightly different. X minus partial X partial Z minus Q partial Y partial Z is equal to Z. Such that P is partial X partial Z is 3Q partial y partial z at x equal to 2. This is another condition. Oh, sorry. This is small p, small q. So we have dx over x minus y over dy c over dz. So first condition, and maybe we can start with this. X over dx is, oops, what's happening? X over dx is c over dz, or ln z minus ln x is constant. That means z over x is u, is some constant, and x over dx plus y over dy is equal to 0, or ln x y is constant, phi is xy. Therefore, u is some function phi, right? Or c over x is psi xy, z is x psi xy. So general solution, u is psi v. We have z is x psi xy. So what about the condition? P is partial x partial z according to definition. That is psi xy plus, this is v, x partial v partial psi partial x partial v psi xy plus x psi dvd. How about q? Partial y partial z is x times dv d phi partial y partial z partial v, right? So that is x squared dv d psi is equal to psi v plus v dv d psi. So at x equal to 2, v is 2y, right? Therefore, t is psi 2y plus 2y dv d psi d psi. So actually this is psi free dv d psi equal to 4 times dv d psi 곱하기 3. So this is 12 times dv d psi. So we have 3 minus 12 dv d psi is equal to psi 3 is equal to 0, or psi over d psi minus 3 minus 12 dv therefore ln psi plus ln 3 minus 12 is constant. Oh, no. This is wrong. So therefore, ln psi ln 3 minus 12 is some constant, or you mean here?
네, 맞습니다. 그 가운데
Okay, that's a very good question. Here, right?
네, 맞습니다.
The z is actually x times phi xy, right? So if we differentiate y, what happens? X, we don't do anything, right? We differentiate this times by using chain rule, d3 over d5. Then we differentiate 3 by y. What happens if we differentiate this by y? What do you get?
아, 맞습니다.
X with x squared.
감사합니다.
dv So this is pretty much about the first two, the differential equations. Any other question? That's a very good approach. I mean, very good question. And then we somehow slow down our approach, right? Psi times 3 minus 12 is some constant. So therefore psi v is c over v minus 12. And since we have z is x times psi v is x times xy minus 12 over some constant. So this is pretty much about the first order differential equations. Yeah.
그러니까 그 PQ 조그마한 소문자 구할 때 V를 Y로 평행분했는데 X가 나온 것 같아서 V가 이해가.
And after first order differential equation, the most second partial differential equation. Relativity free equation of third order, but luckily many of the governing equation for the physical system is within the second order. So we will just need to learn about general second order equation is axyz partial x square partial z bxyz partial y square partial partial x partial y partial square z plus c xyz partial y square partial square z is some function of x fxyz partial x partial z partial y z. Here a xyz b xyz c xyz a continuous function of x, y, z. We are going to consider the second order general second order partial differential equation for constant and continuous coefficient function. So for example, fx is called continuous at x0 if for small epsilon delta greater than 0, fx minus fx0 is epsilon for x minus x0 is less than delta. And classification of the partial differential equation is the following. I'll let you copy this. Okay. partial differentiation. If b square minus 4ac is greater than 0, b square minus 4ac is less than 0, b square, equal to 0, 4ac is less than 0. There's something familiar about this expression, right? You learned that during the middle school, called 판별식, right? But it has a name. It is hyperbole. Parabole. Elliptic. For example, Laplace equation. Partial x partial x square partial z partial y square partial z is equal to 0. So for this example, a is equal to 1, b is equal to 0, c is equal to 1, right? So b square minus 4ac is minus 4 is less than 0, right? So Laplace equation is called elliptic equation. So perhaps you can stop here today and continue next time, right? So quiz is up to today. Today's lecture.